Hiya. I'm going to be telling you about Zooms for a bit. So my name's Callum, but I also go by Cubed online, so you might see that referenced on here. First things first, I'll go through who I am, what a Zoom is, and then we're going to hack some Zooms and hopefully take some questions. Should be nice and chill. So I'm Callum. I'm a lead security researcher. I'm known for hacking the iPod Nano. See my talk at BTEDx from earlier this year. And that's my Feddy and my email if you want to get in touch after. So first, what is a Zune? Well, here's one as an example. I actually brought props. It's an MP3 player. Microsoft released them from about 2006 to about 2011. They made 3 different versions of them, but really there's only 2. We'll get into that in a second. Famously, they lost to the iPod. Basically, nobody had one, especially not over here in the UK. They're incredibly hard to get. All of mine I've had to import from Ireland, which was not exactly cheap. But let's have a look at some Zunes. So this was the first Zune, Zune 30. It came out in November 2006. It has 30 gigs of storage. It's actually got a spinning hard drive in here. It has Wi-Fi but no Bluetooth. No one had AirPods back then. Funny thing is they wanted it to look a bit like an iPod, so they put that wheel at the bottom. That's not a wheel, that's a D-pad. They just wanted it to look like an iPod. It has a Freescale IMX31L CPU, which has a staggering 64 megs of RAM, and famously came in brown. I don't know why they decided to do that. And then they did an update, increasing the capacity to 80 or 120 gigs, made the screen a bit bigger. This came out in November 2007. They also then followed that up with the 4, 8 and 16 gig models that have flash storage, so they don't weigh a ton and have better battery life. And they replaced that D-pad with a proper trackpad, which is a lot easier to use. Internally exactly the same as the Zune 30, so we group kind of all of those together as the Zune SD generation. And again, they still didn't put Bluetooth in them. Then they brought out Zune HD a few years later, in 2009. They came up to 64 gigs of storage. Still didn't have Bluetooth. And have NVIDIA sockets in them, for some reason. It's actually the 2nd generation ever NVIDIA Tegra. And that screen is pretty cool. It's a multi-touch OLED touchscreen, which back in 2009 was really rare. So it's kind of led into Microsoft's Windows Phone era, if anybody remembers that. I specifically didn't talk about the software, though. Because obviously Microsoft released these, it has to run Windows CE, which is really, really weird OS. Doesn't come up very often. If you went to the operational technology talk, some of their kit is probably running Windows CE that they look at. But it's compact embedded. It was designed as a heavily embedded version of Windows, specifically for use in embedded industrial medical applications. So it's still used in places like that. And point-of-sale terminals, if you've paid for something ever, you've probably interacted with Windows CE. It does have some shared lineage with Windows. From talking to some people who've got more knowledge about this than I do, they think it may have came from a fork of Windows 95 or 98. But the kernel is very different to modern Windows internally. The Zune SD is running something between version 5 and 6. It's kind of a weird midpoint where it doesn't sort of line up with either. And then the Zune HD is on standard kind of 6.0. So we can get to some apps, some app stuff. You can write apps even if you're not have been authorized by Microsoft. It has like dev apps, and they're written in C# using the XNA framework, which is a game dev framework. They're sandboxed, so you can't run any kind of natives. You can't write any C or anything fancy like that. The release apps that were available on the store, some of which were free, some of which were paid, are encrypted to protect kind of the IP in those apps. And if you run a dev app on one of these devices, when you quit that dev-signed app, it will reboot the device, because when you go load a dev app, it actually deletes some crypto that's used to decrypt those apps to prevent you from using a dev app to leak these possibly paid apps, to try and get it back to a clean state. And this is the main kind of target for what I'm trying to get, is I want these apps out for preservation purposes, because you can't really buy a Zune anymore, and there's a bit of history back there. Another funny is that rebooting method was actually done by just adding a registry key. So you kind of delete that registry key from your app, and it will let you quit it again, but you can't open normal apps anymore. Now, in 2010, somebody called It's Not a Big Truck found a bug in the XNA framework that allows you to actually escape this sandbox to get code running. In essence, XNA, or C# more specifically, allows you to get pointers to variables through some unsafe APIs, but they've blocked access to read or write to them from the C# runtime. There are SDK functions that don't have those limitations, and there's even one that is just a wrapper around the standard memcopy. So if you put something on the stack, you can essentially cause a stack overflow, and they don't expect you to ever be able to do this, so you can get code execution through that. With this tech, you can now run kind of native code on at least the Zune HD this works on. Security-wise, they put ASLR on the heap to randomize the location of data structures in memory, but they didn't randomize the location of any of the code, and that'll be relevant later. They split user space and kernel to prevent you from accessing privileged data and code, and they did actually employ everywhere except the XNA framework cookies, stack cookies, to protect against stack overflows. And they do have non-execute permission checked as well, so you can't execute code unless you mark it as execute explicitly. As a weird side effect, though, the kernel can patch itself and has RWX perms, but only when you're coming from the kernel, which is kind of going to be useful later. The Zune HD and the SD have a lot of third-party vendor supplied drivers. This was the first area I started looking at when I wanted to kind of own these devices. On Windows CE 5, these drivers are always ran in user space, but because of this weird 5.5 version running on the SD, they've actually moved those drivers into the kernel. So this protection of running all the drivers in user space doesn't exist. There's you can identify these because they've got a K prefix essentially on the file, which tells you they run in kernel space, and that's kind of when you were to start looking. Microsoft did write some pretty good docs on how not to put bugs in your drivers. They've got quite a lot of documents like this. I'll highlight: device drivers should not unexpectedly crash or unexpectedly elevate privilege, which is a hint. But they also had this interesting point, which is that you should check access permissions on nested pointers in ioctl calls. So when you open a file on the Win32 API, you can do something called an IO control, which is an operation on these files that gets handled based on some command ID. And the arguments that you provide, the input and output data, is checked to make sure you have permission to read and write to that data, and you're not trying to do anything you shouldn't. But if those structures that are pointed to then point to other structures, there's no validation on that because it's not aware. It's an opaque memory blob. So you have to explicitly do those checks. And this is what they're highlighting here, is that you need to use those kind of extra check functions before you use them. Do you think Microsoft can follow their own rules? No, they can't. So they actually got it wrong in the same driver twice, which is very impressive. So this is our first bug. It has a hardware-accelerated WAV file decoder in the kernel for some reason, and this is kind of the entry point to that IO control handler, and there's this command ID of 1D00C, where it then calls through to this function. And notably, this from user space in buff. We don't need to do any checks on this because the OS will check that for us. So this is all safe up until this point. Then it comes to this function where it pulls out some fields from that safe pointer. Again, there's nothing wrong with this code. There's no bug here. This is completely safe as long as these aren't pointers. The problem is it uses them as pointers. So the bug actually doesn't come in until the second case here. This first one simply takes a value that we've given it, treats it as an opaque value, and stores it as a member or some structure. But when we send this command after, it will actually take a value that we provided that isn't checked and treat it as a privileged kernel pointer, and will copy that written value out again. This is essentially the read version of this other operation above. So what we can do with this by doing these two calls is store a value somewhere and then write it to anywhere we want in memory. Which the code to do that looks a bit like this. We open the file, which just requires some read permissions, which we have. We send this command, which will save that value. And then send this command, which will write that value out to any address of our choice. And it gives us this kind of write 4, it's a 4-byte value we can write. It also does some other corruption that I'm not including for time. Thankfully, because of this weird 5.5 version of Windows CE, it has a config file that is defined for people that build the OS that can essentially turn off the kernel user mode separation, I think for performance reasons. That file should be read-only and only read once, but we can write anything we want, so we can turn it off, or turn it on. So by simply flipping that to on and restarting our program, it will now run in kernel mode, and we have complete access to the device. It works on every Zune SD, on every Zune SD firmware version as well, which is quite nice. And you can even do it purely from C#. You don't need the C++ C, but we do it by C for reasons. And we can use the same bug to clean up that kind of corruption I mentioned, getting us to kind of a clean state where we've only flipped that one flag. We can move on to Zune HD now, now that we've done the early one. You'd think it would be harder. The problem is, this might look familiar. It's the same handler in a different driver. This one's written by NVIDIA rather than being written by Freescale. But has essentially the same control flow. Comes into here. This one's actually nicer, because when we send in command 13, it just writes to a fixed offset for a pointer that we control, a value that we control, which is very nice. We don't even need two calls. So this is yet another write forward. There is a limitation on this. We can only do this once, due to some other checks, but we only need to do it once. The export looks a bit like that. Open the file, send the command. This doesn't work in the Zune SD, it only works in Zune HD because the Zune HD is the only one with an NVIDIA SoC. The question then comes of where do we write with this single-use write? But the kernel has this very nice table it maintains where it tracks the types of arguments to system calls. And the reason it has this is to kind of check if those are sensible values when they're coming in. So if you pass something marked as a K pointer or kernel pointer, it will check that it's actually a kernel pointer and not just something that you've provided. It also has support for just an int type that doesn't get any checks, and thankfully int is type 0, so if we can write a 0 into this table to anything that returns into a pointer, we can allow it to write to any pointer, including kernel memory. There's a lovely function called getExitCodeThread, which simply takes the return value, which you can set if you spawn a thread, and puts it at a pointer. So that's the one we use for this. So the code looks a bit like this. You create a thread, passing in a value. That val gets passed in as x into that function. We then call exitThread and just essentially return that x value, and then call getExitCodeThread, but can pass kernel addresses to write to those kernel addresses. This gives us a write for that we can use multiple times, but we're still limited to only writing 4 bytes at a time, which is a little bit annoying. So we can use that to put some code that gives us a single byte read and write function, and just find one of the unused syscalls that normal apps aren't supposed to be able to use, and overwrite it with this code. So this gives us control of the kernel of both the Zune SD and the Zune HD. Now the question is, could we use this to make apps? It would be really nice if we could find apps that use native code, so we could untether these bugs from having to go through XNA. Sadly, it doesn't work. They're all written in C#. And as I mentioned, they're encrypted. Maybe we could dump them by just launching them and reading their files out from memory. The problem is this hardware crypto engine. Essentially, the keys are stored in this hardware unit, and when you load dev app, those keys are nuked from memory, and you have to restart the device to get them back, which requires going through a fully secure boot chain to get all the way to the OS. So we need a different way in. Thankfully, browsers are hard. Browsers are really hard. Browsers are buggy piles of crap, to be honest. And the Zune HD has a browser, and it's based on Internet Explorer 6. Which, at the time, to be fair, that was not as bad, but it also has a lot of CVEs, but we don't have to find our own bug. This is a CVE that was actually found in the wild by Project Zero, I believe. Essentially, the bug here is there's this arguments variable in JavaScript that, when you call a function, contains all the arguments to your function as an array. But you're not really supposed to write to it. It's supposed to be read-only. And if you do write an object to it, it'll remember that object, but it doesn't tell the garbage collector in JavaScript that that value is referenced there. And this is kind of a problem, because the garbage collector is going to come around and look at that object and not think anything points to it when something does, and it's going to delete it. And that creates a condition that's called a use after free. And use after free are very, very nice when it comes to generating exploits like this. So we can use it to build a really powerful read primitive. And essentially we have strings that consist of a tag and a pointer in memory, and then that pointer points to, for a string, points to a large number, and then it looks after that number that many bytes, and that's the string data. So if we simply find a large number, which we can do that by looking at the code, which isn't protected by ASLR, we can create a object, store it in arguments, it will then get deleted, create lots of variables, and hope that one of those variables that we create will overlap that now deleted object, and then try and use that argument's value afterwards. And hopefully it will pick up the value that we placed in memory and start using the pointer that we give it as a string. And because we can create a very, very large string, we can create a string that covers 4 gigs of memory. We only have 64 megs, so we cover all of RAM, which is very, very nice. We can't read things that aren't paged in, and there's some other limitations, but it doesn't really matter. This is kind of the perfect read primitive. Building on top of that, we can kind of start to leak pointers to structures. So this is a bit complicated, but there is thread local storage. The browser's JavaScript engine is multi-threaded, so it stores the kind of root class that handles all the garbage collection in thread local storage, which is at a static place, so we can go find that. We can find this garbage collector. We go through that garbage collector, and it has these structures called scavengers. And scavengers track variables, essentially. They contain all the variables that are being monitored. And there's a specific type of scavenger called a scarvar list, which tracks an array of variables. So if we go through this list and we find a scarvar list which contains magic values that we can put in a list, we can then find the pointer for an arbitrary object in JavaScript, which is very, very powerful. The main trick here is at the bottom of creating a sort callback, which is how you sort a list in JavaScript, because it will take the list that it's given and create a dedicated scarvar list to track that list so that it's not deleted while it's running a function that does the comparison operation in the loop. So with this, we can place objects in memory, get their pointers, and use those to build structures that reference other structures in memory. This kind of generic primitive, being able to get pointer to a JavaScript object, often called address of or addr of. If you've read other write-ups for JavaScript bugs, it comes up a lot. So now we can actually get some code execution, because we can create a relatively convoluted stack of objects by creating a fake pointer table, having a native object that points to that, and having a variable that points to that. And reusing the useAfterFree from before, we can spray that fake variable. And hopefully, if we try to do operations on that, it will have overlaid our fake variable over the deleted variable. And if you try to use the type of function in JavaScript, the way that works is, if it's a known object type, like a string, which is type 8 from before, it will simply return the string. But if you have a native object, which is a special object used to define JavaScript classes that are implemented as part of the JavaScript runtime, so things like regex or the string class itself, it will call a pointer on that class to ask it to describe itself. And we can abuse that by making that fake vtable we create, making the type of function on that vtable point to anything we want. So we can control the program counter, making it jump to something that we control. It's worth mentioning you have to do this kind of backwards for the order it is here, because you need to create the fake vtable to get its pointer, to then put it into the native object, etc. Finally, we can do a bit of ROP. So ROP is return-orientated programming, and essentially this is, we build a fake stack in memory and have it execute as if it's returning from a very deep call stack, where it will return, we'll do some operations and then return up the stack to the next function, which we will make point to something interesting. So I can use this gadget, which is essentially loads all the registers, which is the perfect gadget. We will set our fake stack up such that PC points to this virtual protect function, which is the mprotect function of Windows. We can change the permissions of memory to make it executable. This is how we bypass the no execute mentioned earlier. We give it some code, which we will simply create a big string with some code in it, and get its pointer using the address of primitive. We can set that 1 is 1 byte, which will be rounded up to the minimum size, which in this case is, I think, one page, which is, I think, 4096 bytes, and then set it to be read, write, and executable, which is kind of the key thing here. And then because we also control the link register here, which is the return address register used to always store the return address from a function call, we can set that to the code that is just protected. So in effect, virtual protect will think it was called from the code it just protected and will return into that code and start executing it. And from that, we can run whatever code we want. For example, we could place a file, like an exe file, onto the storage and simply load that file. Because that exe hasn't been loaded through XNA, the keys are still intact, and we can dump the apps that we want to dump. So, I have a demo, and hopefully the video works. If I can find those. There it is. Give it a second. And there we go. So you can see there at the top it says leak work. That's indicating that block string, and then these pointers it's printing out, where it prints various addresses. This is it dumping the addresses of those structures as it's building them in memory. And then right at the bottom, which you can't see under the notification there, it's saying that it's going to try execute something, and it was running random FTP server as a test. And then if we exit out of this, open up app, we can use that FTP server to dump the contents of that app. And now we have a full backup of all of the apps from the Zune AD, at least all the apps that I could find. In conclusion, Zune, boom. Any questions?